Thank you very much, Pablo. Well, according to Avila, Lubitsch, and Shane, for Lebesgue, almost every parameter in the plane, this unicritical map with integer exponents, this family is either hyperbolic or infinitely renormalizable. So the obvious question is, what prevents this theory to carry over non-integer exponents? So in this setting, today I'm going to talk about Kleinian groups, rational maps, and this specific family, with some results concerning thermodynamic formalism, house of dimension, conformal iterated function systems, which are some way hidden in this form, rigidity and hyperbolicity and structural stability. And this work in particular, it was developed with Daniel Ismania, which was my advisor. And there is a whole theory which is the current project right now, which is to develop a theory of renormalization for these maps. Of course, the first question is, this is not a single-valued map. So that's the main question. So I would like to thank this opportunity, especially for Pablo, for the invitation, the organizers, and I would like to wish Professor de Melo as well a happy birthday. So Kleinian groups are discrete subgroups of Möbius transformations. And it turns out that if you pick a single point and you compute its orbit under the action of the group, the set of accumulation points is going to be invariant. So it doesn't depend on the initial point that you choose. Here we have one example, which is the Apollonian gasket. And the Julia set of a rational function displays the same behavior when it concerning backward iterates. So here we have a dynamically defined object, which is the closure of repelling periodic orbits. And we have the limit set as well, because if you take, there is an exceptional set in the Riemann sphere consisting of one or 2 points. And if you take backward iterates out of this point, this set is going to be adherent to the Julia set. And so this is quite interesting because although it's a basic part of the theory, the fact is that if you take just 1 point, you can compute a chaotic dynamical system and a very intricate geometric structure as well, which is the main motivation for renormalization, as you can see in the picture. So holomorphic correspondence is another type of holomorphic dynamical system. It's a multivariate map, but it's not arbitrary because it's ruled by an equation, a polynomial equation. So for each z, we have a finite number of implicitly defined values of w. And of course, one classical way of looking to these equations is to consider the Riemann surface. And for example, there are a bunch of classes in holomorphic dynamics where you consider, for example, the logarithm. It is a multivariate map. And in fact, it is this property of the logarithm that makes it possible to construct the whole theory of analytic functions, because it's not single-valued. So not being a map, in a sense, is not a disadvantage, provided you look in a precise way. So for example, this, when you take beta, for example, to be a rational number, and you consider z to the power beta plus c, this is a holomorphic correspondence or a Riemann surface with just one branch point. Finally generated Kleinian groups are particular instances of these holomorphic correspondence, because we can collect the whole information of the group into a single polynomial equation. Rational maps in the same way. And so just to remind, we have this picture for this dynamical picture for the rational map. And according to Pura and Penrose, we have this picture for these holomorphic correspondence. So you can see we don't lose anything at all when it comes to geometric structure. And the natural question is, are there Kleinian groups and rational functions? Do they make all the classes of holomorphic correspondences? Because all of these two are part of the same class. So the question is, no, because we can actually construct some holomorphic correspondences which are, in a sense, both types of dynamical systems. And this is the subject of this paper with a follow-up given yesterday by Luna, where this, according to my interpretation, is a very interesting explanation of hyperbolicity conjecture via the question of matings. Because if you construct a family of matings parameterized in the Mandelbrot set, then you can translate all the classical problems to this setting. So what prevents this to be studied in this case? Of course, a theory of hyperbolicity, which is not yet developed on its full interpretations. There are some just partial results in the literature. And a theory of renormalization. I have worked on this, and I'm just starting to do this. So what's the definition then of Julia set for these type of maps? You're free to choose a particular orbit, but whenever you choose one, you can close it and compute the branches. You compose and compute the derivative. This is the multiplier of the orbit. So you can define a repelling or attracting according to this property. Here, for example, have repelling periodic orbits. In the same way, you can define a dual Julia set, which is just the same computation, but now we require the multiplier to have modulus less than 1. And often, this set is completely uninteresting, or, well, I shouldn't say uninteresting, but the fact is that for rational functions, it is always finite. This is just a finite set of attracting periodic orbits. But it turns out that for this type of holomorphic correspondence, these sets can often have the same structure of the Julia set. So we can be topologically mixing when it comes to backward images. And it can be used to establish rigidity results in one-dimensional dynamics as well. Not for iteration, forward iteration, but for backward iteration. So, and indeed, the dual Julia set is just the Julia set of the inverse map. We can define the post-critical set in the same way, which is just get the critical point, compute the orbits, the future orbits, and then take the closure, forgetting the initial point, which is exactly the critical point. And this is the post-critical set. In the theory of holomorphic dynamical systems, the post-critical set plays a very important role, and here in this setting as well. So you can define hyperbolicity, you can find, you can use Schwartz's lemma in this context as well, provided you have certain control of the set. And we define the set of accumulation points of this with this notation. And we have a characterization of a strong hyperbolicity, which is the case when we have just a finite set, which is something similar to the case of polynomials. We have just a finite set of attracting periodic orbits. And when we impose the condition that the post-critical set is accumulated in this finite set of orbits. When this happens, we have hyperbolicity for polynomials, but here we put another, we call this condition of a strong hyperbolicity. And we're going to understand in the next topic why we say this is strong in this case. For the quadratic family, the set of strongly hyperbolic maps, according to this definition, is an open set inside the Mandelbrot set. So it is an open set by the definition actually not only for the quadratic family, but in this case especially. And a very difficult conjecture in the field restated says that the interior of the Mandelbrot set is exactly the set of parameters where this map is strongly hyperbolic. And this is implied by the local connectivity of M. So the conjecture is that the interior of this figure is the black part. And of course this is open, but we have rigidity when we study non-integer exponents, while strong hyperbolicity occurs in an open set of parameters for the quadratic family. For this non-integer, this is a discrete set, so it is impossible to deform this type of correspondences remaining in the same hyperbolic class. So in a certain way, you have to extend the notion of hyperbolicity, or either you extend the notion of hyperbolicity or you have a rigidity result. And the general principle to establish this result is that in this setting, weak forms of occurrence near the critical point produce countersets and conformal iterated function systems. So this is a very interesting because this correspondence is a natural source of other types of holomorphic dynamical systems. So you start with something which is not a polynomial, but just with a rational exponent, and you obtain another type of conformal dynamical system, which is iterated function systems. So you have this pictorial picture. We start with just one point and we iterate, and suppose that we come back very close to it, say in an epsilon neighborhood. So what happens to the future iterations? Well, if this point is the critical point, then something very interesting happens, because the correspondence is given by this. So here we have the Z plane and here we have the W plane. For each Z, we have exactly Q values of W associated via this equation. So for Z equals to 0, for example, what can you expect? The solution, you put 0 here, and the only point associated is C, the parameter. But if you put another value close to 0, then you're going to have what? The branched values of a Riemann surface here. So when you put a curve, say with just 1 as a rotation number, it gives P over Q, it winds here. So we can say that for each point to have exactly Q values here because of this property. So for small domains, this correspondence is going to map one simply connected domain into, say, Q, in this case, 4 other domains. This is just simple iteration. There is actually no theory involved here, just observation. What happens under iteration? And so for each D containing domain, we have a finite union of other domains. And so if we start with this point, this domain here, under iteration we produce other 4. And then we have a non-singular branch here, it produces 4 and 4. And what happens when it comes back, because it is a weak form of recurrence? What can we expect this in this part of the picture? We obtain exactly where we have this. We're going to have under composition this set of maps of the disk into itself, and by Chauvat's lemma you have a contraction, a strict contraction of these in the hyperbolic metric. So we have a conformal iterated function system, and if you persist iterating, you're going to obtain a counterset of attracting periodic orbits. So just to recall, we start with just one point, and on iteration, we're going to produce a counterset precisely here, which is given by the limit set of this system. And so the rigidity result established here says that if you have just one point where this is strongly hyperbolic, then all nearby points are not going to be strongly hyperbolic. We have the two Julia sets are going to be disjoint. The dual Julia set is going to be a counterset. We're going to have an expansion of a conformal metric in one of them and a contraction in the other. But the simple fact that this jumps from the finite case to a counterset establishes the rigidity. So you deform a finite set and it becomes a perfect set. So this is a rigidity, geometric rigidity coming here. For limit sets, you can consider backward iterations and accumulation point of pre-orbits on the F. And here we have one example. And for these correspondents, we have these quasi-arcs, and a session, a transversal here, is going to produce a counterset, usually. So the limit set of that correspondence with a non-integer exponent is not going to be a quasi-circle anymore, but actually the projection of a solenoid, as you can see. Under the picture, you can see that this is a projection of a solenoid. And a similar statement holds for backward iterates, but I'm not going to explain it here. The main fact is that we can actually provide some examples, because this is just a bunch of theoretical results. But we can produce some, not exactly a pure holomorphic correspondence, but a semigroup of rational functions. This translates onto these semigroup with just two generators. And here we have a set of parameters, which is contained in the unit circle. And when we increase n, this set becomes dense, so we have a dense set of examples. Set of examples where the correspondence, this, is strongly hyperbolic. So we have, under this observation, we have a set which is discrete, but it doesn't imply that it is not interesting. So it is discrete but non-trivial. And theorem A provides an initial picture if you're interested in computing the bifurcation locus. You start with some points and you make a deformation, and with this you construct some disjoint sets. And the question is, what kind of a structure can you expect to find when you perturb these initial points? In the case of quadratic family, of course, you're going to obtain the Mandelbrot set. But in this setting, we can actually show that for every Mandelbrot set, you can construct a bunch of examples. And the main idea is that for each point at the center of a component, So for each point here, for example, for each point here and here, you can compute, and here, you can compute, you can generate a strongly hyperbolic example of correspondence. So we can put all the multiple sets together to generate bifurcation locus. So we obtain a set which is discrete, but as it is drawn in this picture, it is discrete, but discrete just because it is not compact space, because we have accumulation points out of the set. So it is discrete but non-trivial. And one thing that supports all this theory is that actually Julia sets in this family are just projections of Julia sets for maps of C2. So if you increase the complex dimension for just one, you obtain that these maps, multivariate maps on the plane, are actually projections of other types of behavior in the two-dimensional complex space. So these, if this Julia set, for example, if this is hyperbolic, and this is a Julia set in the plane, then there is a holomorphic map acting on the mains of the two-dimensional space, whose Julia set projects onto this Julia set. So what we are observing is just a projection of something which is happening in the other dimension. And this projection is actually a semi-conjugacy. So the first question is, what kind of map is that produces the Julia set of a correspondence? There is a strong interest in that, because obviously we can see the correspondence acting in the plane, but you cannot see the four-dimensional space. And this map is locally a skew product. So for each point in the domain, we have implicitly defined a branch, and this branch defines locally a skew product. For example, if you have the quadratic family, we have a map which is defined in the whole C2, and it's given by this formula. So the dynamics of this map projects into the dynamics of the quadratic family. You can perform holomorphic motions of these. So we have a whole theory already developed in this sense. For maps of C2, we can define an holomorphic motion. Any structural stability. And for parameters close to the origin, this is holomorphic to the solenoid of Williams-Smale, whose construction is given by this. So this is the solenoid. Actually, our solenoid is not the solenoid, but the union of lots of connected components, which are these solenoids. And this phenomenon was already described in Besson similarity with the result established by Hubbard and Oberste-Vogt for NL maps, where they prove that this is a solenoid for parameters close to 0. Indeed, if Q equals to 1 and P equals to 2, in this case, the bundle map admits an extension to the C2 space, which is a skew product given by this. And it was proved by Hubbard and Oberste-Vogt that for this quadratic family, if this is expanding on its Julia set and B is sufficiently small, then this map is hyperbolic on its Julia set, and this is topological conjugate to inverse limit. And recently, Ishii and Smiley proved that for C equals to 0 and B minus than this upper bound explicitly given, the Julia set is topological conjugate to a solenoid. So this is establishes a sort of dictionary between our theory and something which is already developed for NL maps. So the projection of the holomorphic motion determines a normal branched holomorphic motion on the plane usually set. And this theory is already well developed in this paper of Desjardins and Ubich, where they defined branched holomorphic motions to study the stability and bifurcations for automorphisms of C2. And for more about this, we have a recent paper just submitted to arXiv in August, where we discuss more of these relations of holomorphic motions in the C2 space and the projections in the plane. And the main idea is that if we make holomorphic motions in C2 space, and when we project, we're going to obtain holomorphic motions of arcs. So all of this is an holomorphic motion of something, as you can see. For house of dimension, I just want to mention very roughly some results, is that we can actually apply the thermodynamic formalism to determine the statistical properties on these. And this is a very beautiful part developed by Well in the theory. We can actually develop the same thing in the setting. I'm not going to explain it all. So we have topologically mixing maps. Under these, we can use the thermodynamic formalism given by the Perron-Frobenius operator to develop a sort of Bowen formula, which is the zero of the pressure function is going to give an upper bound for the Hausdorff dimension. When, for example, one corollary of this theory is that if you take the square of Q minus the P, then this bound is strictly less than 2, and as a result, the Julia set has 0 Lebesgue measure. This establishes a sort of a dictionary between Riemann surfaces, dynamics, and we could put here holomorphic correspondences as well. Something in the middle, actually, because holomorphic correspondence can be viewed as a Riemann surface. And there is a classical theory already developed that for the action of a quasi-Fuchsian group, the limit set of a quasi-Fuchsian group is a quasi-circle, like this. You can see in the paper of Bowen about this. And Well, in 1981, proved that the Hausdorff dimension, there is a formula for it. So this establishes the geometric rigidity, because for parameters greater than, different from 0, you have actually you have a quasi-conformal curve. The Hausdorff dimension is strictly greater than 1. And here we have the same rigidity, we have almost the same results, but with just bifurcation that makes all the arcs being a quasi-conformal deformation of the universal cover. So this is a dictionary between. So this is just a part, as we're going to, I was discussing in the initial of the talk, this is just the initial part about hyperbolicity and structural stability. And just to summarize, there are some connections between the dynamics on the plane and locally defined skew products on a C2 space. And that weak form of recurrence that determines a conformal iterated function system, in my opinion, is just the beginning of renormalization, because you can see that recurrence as the inverse of what you expect in renormalization. And this is my current project. So thank you very much for the attention of everybody.